There we go. Okay, welcome everybody to tonight's talk on the geological storage of hydrogen for net zero. And I'd like to introduce Professor Katriona Edlmann, who is a Professor of Sustainable Energy here at the University of Edinburgh and has got lots of research experience in the secure and sustainable utilization of subsurface for low carbon energy applications. And that includes hydrogen and CO2 storage. So Katriona studied at Aberdeen University first before taking her master's at Heriot-Watt and then also her PhD there as well. And she's responsible for several bodies in the UK and industry funded projects investigating underground hydrogen storage technology. And just reading the list of the bodies she's on and the groups she advises includes things like the International Energy Agency, the House of Commons Scottish Affairs Committee, the UK Government Department for Energy Security. It's quite an impressive list here. So I think we're in for a real treat tonight for the talk. And I hope we're all going to learn a lot about the geological storage of hydrogen for net zero. So, Katriona, thank you.
Thank you very much. Thank you. Thank you for that kind introduction, which I wrote myself. And it's really lovely that Pat Corbett's in the audience as well. So Pat was the leader of the master's degree that I did and really, I guess, set me on this journey, really. It's your fault I'm here, Pat. So yeah, it's a real joy to speak to you all about really the role of hydrogen in supporting net zero. And there might not be as much geology as I'd like to show you. I have a few slides at the end if we have got time to do a wee bit more of a deeper dive into geology. But really, this is kind of giving you a bit more of a scene setting and an appreciation of really the challenges ahead as we try to move towards net zero and decarbonise our energy. And of course, it's not just me that contributes to this. There's a whole host of researchers and amazing people at Edinburgh that have contributed to the hydrogen research at Edinburgh. So we've really got a spectacular team of researchers who have just done an incredible job in raising awareness of this technology. And we've done this in a very short period of time. So it's a pretty exciting field to be working in. So, we all know what the issues that we're facing at the moment. There's too much CO2 being emitted into the atmosphere, which is enhancing our climate change and causing significant problems. And to really understand how we can deal with this, it's really important to kind of reflect on where are those CO2 emissions coming from, because that's where we get to the root of the problem. So the pictures on screen to you, I never know my left and my right to that side. We have the global picture, and to the left, we have the UK picture. Now, what that's showing you is the source or the sector that is responsible for our CO2 emissions. So what you can see globally is that all the kind of shades of blue, these are kind of emissions or CO2 emissions that are coming from energy. Yeah, so you can see that takes up a pretty hefty portion of that pie chart. Really about 75% all told. And then the picture is no different in the UK. It's really very similar across the world. That, the use of the burning of fossil fuels for energy and other applications is responsible for about 3/4 of our CO2 emissions. So that's a big problem. So let's try and tackle that. So that's really the kind of motivation behind decarbonising energy, because it is such a large contributor to our CO2 emissions. And that's kind of what forms the framework of the work that a lot of us do in Edinburgh and universities and places all around the world. So let's look at how we're doing, because we have signed up to the Paris Agreement. We do have net zero targets. We have these kind of obligations and we have an awareness that we need to do something. And steps are being made, really positive steps forward are being made. Now, I quite like this graph, which was put together by the Carbon Brief, because it really, it's a bit speculative, but what it shows you, I think it tells the story very well. So if we look at the big red line, that's sort of tootling along and then drops very dramatically in, just after 2013, something like that. That's the electricity. And that is the carbon emissions, millions of tons of carbon emissions from that sector. Now, of course, this was an easy change. We simply closed our coal-fired power stations, or we switched them to gas. So, that was a quick and easy win. We looked great, we met our targets, we were looking great on the world stage, we were doing a really good job of decarbonising. And that's excellent. So we've improved energy efficiency, we've changed our light bulbs to LED, and as I say, we switched from coal to gas power generation, and we have renewables. That is also a part of that success story. But of course, all the other sectors, are really challenging to decarbonise, and we're really not making the progress that we need to. So whether that's in transport, whether that's in industry, services, refineries, all of these other sectors, these are hard to decarbonise, they're hard to electrify. And that's really where, again, we really need to kind of focus our efforts in, because to reach net zero, we haven't got anywhere to hide anymore. It was fine when it was just, well, we'll try and keep global temperatures below 1.5 degrees. Then you could say, well, we've done a bit. We've closed our power stations, or we've switched to gas. We've reduced our emissions. Aren't we brilliant? But net zero means we have to do the hard stuff. And that's really why we have to be a little bit more creative about the solutions that we have for decarbonising energy. So why is it so difficult? It's really a very challenging, it's a very big challenge that we face. And I think this graph, which is by Grant Wilson, a superb researcher at Birmingham, who's just amazing at visualizing data. So I just downloaded that today, so you have the most up-to-date figures. But really that shows you the picture of energy use in the UK. And I think it sums up the challenge really well. So what you can see is the green wiggly line, that is our renewables. So the graph runs from sort of beginning of July in 2021 to April 2020, or March 2025. And the axis is gigawatt hours per day of energy use. So gigawatt hours per day. So you can see, the renewable energy is ticking along a little bit, increasing a little bit over time, which is good. The red wiggly line, that's our total electricity demand. So you can already see that there's a gap between the renewable electricity and the total electricity we use. So that's a challenge. That's the first challenge we've got, is bridging that gap. And then on top of that, we've got that blue wiggly line that's going in and up and down over the winter and the summer. Now that is our gas use, because of course the majority of our heating, the majority of our use is from natural gas. 80% of homes, or more than 80% of UK homes, are heated by gas. But the challenge with that is, of course, that it is a very seasonal change. So we can look at going from, maybe 2,000 gigawatt hours a day up to 4,000 gigawatt hours a day in a couple of weeks, depending on the weather. So that's a very, try to do that with renewables. That is a really big challenge to achieve. So we've got this huge discrepancy of this interseasonal demand for heat, which is very difficult to decarbonise. And then on top of that, we've just got trudging along in the black is our transport use, sitting around about 1,500 gigawatt hours per day of fossil fuels. I mean, yes, there's a few more electric cars on the road, and how lovely if you've got one, but it's a very difficult area. So, we've got this picture, which is quite challenging and shows you the thing ahead. So I guess, first and foremost, what we really want to do is drop our demand. We want to stop the demand and drop those curves so we don't need to use so much energy in the first place. But of course, that requires changing habits. And that's really difficult to do. It was quite interesting after COVID, the travel had stopped, the stats looked great. If you plotted a graph at that point of emissions, it was dropping down. Oh my goodness, have we recovered and gone back on holiday like nobody's business? So, we didn't learn anything. We're back worse than where we were before in terms of our energy use through travel and all these other things. So, changing habits is difficult, but we can do it. Reducing our transport distances, energy efficiency, insulation on our homes. These kind of steps, but they're not cheap, they're challenging, and they require us all to make that effort, which is sometimes quite difficult. And then, of course, if we're really thinking about full electrification from renewable energy, which is really what we want, how do we manage to do, first of all, how do we ramp it up so that we can deliver simply our electricity demand? And then on top of that, we've then got to do transport, and then we've got to suddenly do that interseasonal demand for heating. So that is a lot for our renewable energy industry to do. And I mean, we are making great progress with renewable energy, and it's fantastic. It's becoming cheaper and cheaper because of all the incentives that were put in place many years ago, and we're rolling that out. But one of the things that's so challenging already, even with the small amount of renewable energy that we have deployed today, is that our electricity grid was not designed for renewable energy. Yeah, so basically the cables just aren't up to scratch. They're just not thick enough to take the large amount of energy that we can produce from renewables today, let alone in the future. So what we find often is that we have to switch off the turbines, and we just can't generate the electricity, even though we could. Perfect conditions, we could be making that electricity, but we have to switch the turbines off. And that's because either there's too much power going down the lines and they simply can't take any more, or it's 4 o'clock in the morning, everyone's asleep and the energy just isn't needed. So we've got no way at the moment of using all that energy. And the problem is that then gets wasted. And that the term for that is curtailment. Now the maps on the graph, on the screen, the dots reflect, the top one is the amount of energy that's curtailed, and the bottom graph is actually how much it costs. So as well as the fact that energy is wasted, the wind farms also get paid because they're having to switch off their wind farms. And of course, that was part of the original subsidy, because nobody would invest in a wind farm if they knew that most of the time it can't get delivered to the customers because the route to customer wasn't good enough. So, there was an agreement put in place that, we can build the wind farm, and even when it's windy and you can't deliver it to the customers because the system isn't built for that yet, we'll still pay you for that. So of course, that did mean that people would invest in these businesses. So it was necessary. It was a necessary subsidy. And it has worked because it's brought the cost really far down, but it's causing now quite a lot of money. So we all pay about £10 a year to cover the cost of this curtailment. So it just goes to waste because we've got no energy storage at all. So in 2023, 4.36 terawatt hours of energy was wasted. It's a phenomenally large amount of energy that could have been delivered to the grid, could have been used, totally wasted because we've got nowhere for that energy to go. There is nowhere to store electricity at that level at the moment. So that is really a big challenge, and that's what we need to address. And you can see from the map, it's not surprising, most of the curtailment's in Scotland, but that's because England had a moratorium on building renewable, onshore renewable energy, whereas Scotland was happy to, well, I don't know that the residents were happy, but there were lots of renewable wind farms put onshore. And of course, as we build out the big farms offshore, the curtailment is not going to get any better. So it's going to get worse and worse and worse unless we find a solution to balance the renewable energy supply and demand through energy storage, and then reduce that curtailment wastage. And that's where hydrogen comes in. Yeah, so hydrogen is a very versatile kind of energy carrier or energy vector. It can be used in much the same way as natural gas, but what it's really good for is supporting the renewable energy system. So what it can do is provide that large-scale energy storage. So we don't have to have any more wastage. That energy could go to generating hydrogen through electrolysis, and then that hydrogen can be stored, which is where you need the geology, which I'll get to later. But then it can distribute that energy whenever it needs to. So it's a really useful tool for that. So it provides that interseasonal storage, it reduces curtailment wastage, and it helps system resilience and energy security. This is homegrown energy, really lovely. Renewable energy, generate through hydrogen through electrolysis, store it. You've got this really sustainable and homegrown energy that you're not needing to ship in from anywhere else. The other thing that hydrogen can do, which is why people are also interested in it, is there are some sectors that are really hard to electrify. With the best will in the world, there just isn't an electric option at the moment. And of course, electricity from renewables is what we want to use, but it doesn't work for large scale, it doesn't work for shipping, it doesn't work for aviation, it doesn't work for long distance transport. Really doesn't, we have to have clean feedstock for our industry. So let's capture some CO2, let's make some hydrogen. They just need a C and an H to make a lot of the feedstock for our industry. We don't need to be taking it from the subsurface anymore. Obviously, we've got heat, which is a bit of a kind of touchy subject sometimes. It can also help industrial use, industrial heat. It certainly can help decarbonise power generation. You can burn hydrogen in the same way as you can natural gas without any emissions. So it really can help hydrogen to power. And then, of course, what it can also do is support the development of CCS. And that's because another way of generating hydrogen is by steam reformation of methane. But normally, that's a very carbon intensive process because you split this C and the H4, you get your H and you just emit masses of CO2. So the idea being that we can capture that CO2, store it, and that's called blue hydrogen. And then, of course, suddenly the cost of producing the blue hydrogen incorporates the cost of carbon capture and storage. So suddenly we've got a way of paying for CO2 storage, which we haven't had up until now. So, you know, that you can see why people are kind of interested in hydrogen and its flexibility. And that's really reflected across the world. So globally, there's 60 countries or territories that have now got hydrogen policies in place. And that covers covers all of the, 82% of the global CO2 share, energy-related share of emissions. So people are really kind of thinking, oh, this is really quite helpful. And most everybody's future energy modelling scenarios, including the UK, they can't reach net zero without some contribution of hydrogen to support the renewable electricity industry. So you can see that, globally, everybody's very excited about hydrogen, came on the scene in 2017 when Japan first adopted a hydrogen strategy. And as I say, now we've got 60 countries. This is happening so fast, which is kind of cool. So this picture, whoa, this is just a snapshot of the UK hydrogen policy landscape. It is almost impossible to keep up with all of the policy documents that are released almost every day. This is just some of them. I couldn't possibly fit them all in. But it really shows you that evolution of how the UK is viewing hydrogen. It's viewing hydrogen as a way of transitioning our North Sea, which is really important. It's viewing hydrogen for industrial decarbonisation. It's a very important role in that. It's looking at it for heat. It's looking at it for transport. Obviously, we had the invasion of Ukraine. Suddenly, energy security was massively on the radar. So that we had the British Energy Security Strategy, and actually in that strategy, that doubled the ambitions for hydrogen because there's a recognition that that is really a homegrown energy that stops us being reliant on imported gas. So now we have money being spent to produce hydrogen, to store hydrogen, to transport hydrogen. So there's all these business models in place and a hydrogen net zero investor roadmap. So the government is starting to put money to support all of these policies for hydrogen. So it's not really going anywhere. And it's really important that we give investors confidence that there will be a hydrogen market so that all of these projects go ahead. So as I mentioned before, no future energy scenario meets net zero without some contribution from hydrogen. And in the UK, we anticipate, or the UK government anticipate that being between 20 and 35% of the total energy mix. Now that is the equivalent that electricity is today. So it's now, today we have about 20 to 30% electricity, 70 to 80% natural gas. So in the future, by 2025, for a net zero energy system, we'll be looking at 20 to 35% hydrogen and the rest as renewable electricity. So, this is a really important kind of aspect of our future energy scenario. And that really is the kind of government statement on how that's going to be. So I mentioned how we make hydrogen, and I've already kind of gone through them. I always like to show and tell. So over here is my little electrolyzer. So this is water with universal indicator, if you remember from school. So it's green when it's neutral. And then I'm just going to attach a battery. So I'm doing a cathode and an anode. And we're going to electrolyze the water in here. And I'm going to produce hydrogen as we go. That's it. Job done. So we've got, at the moment, most of our hydrogen is produced from the steam reformation of methane. So we just reform natural gas. And as I say, masses of CO2 emitted with that. It's responsible for about 600 million ton 600 million tons of CO2, so almost twice the UK's annual emissions just from making hydrogen. And of course, it's used in fertilizers and industrial processes to clean up gas, to clean up oil, all of these other things. So hydrogen already has a very important role in society. Anyway, the problem is we make it it's very dirty because we don't capture these emissions. And it's, you know, relatively efficient, relatively cheap. You know, we make a lot of it. It's a very well-established industry. You know, that's fine, but it really is very high emission. So we have to, first of all, reduce the emissions from our from our grey hydrogen. So one of the ways we can do that is by capturing the CO2 at point sources. The great thing about when you're making grey hydrogen is that it's a point source. So you can capture these from these industrial settings, and then we can store them. And I'm sure you've had many talks about CO2 storage here. You know, that is a very well-known technology, which is, you know, geologically, we can do very well. What's been very challenging for CO2 up until now, or CO2 storage up until now, is paying for it. Yeah, that business model for it, because the carbon taxing hasn't been enough to really incentivize it. But of course, now it's going to be part of the cost of blue hydrogen. So suddenly, you know, what you can see, which I think is quite interesting, is the cost of grey hydrogen is 0.7 to $2.4 per kilogram of hydrogen produced, whereas the cost of blue hydrogen is between 0.15 and 4 kilograms per hydrogen. So the difference between those two is the cost of CO2 storage. Yeah. And there's lots of subsidies in place now to make sure that they are cost comparative. So people will buy the blue, and it will bring the, you know, it will force the grey hydrogen to become cleaner, because people will want the blue hydrogen. And the UK is taking a twin track approach to this at the moment. They are looking at blue hydrogen and then green hydrogen. So green hydrogen is what we've got generating over there, which is basically splitting a water through electrolysis. So at the moment, it's not a very well established, I mean, it's a very well established technology, but it's not rolled out at scale. So obviously its cost is more because it's a new, you know, we don't do it on a very, very large scale. So all of that has to scale up. And that's exactly what happened with wind farms. You know, when you think about the initial, you know, the size of the turbines they made right at the start of the beginning of the industry, and the ones now, like these are little tiddlers in comparison with what they have now. So, you know, that really, those learning curves, that technology rollout, economies of scale really drive those costs down. And it's absolute, and there's so many incentives across the world to drive that cost of hydrogen down. So, you know, it's expected to fall to $1 per kilogram by 2035. The US has a hydrogen Earthshot, and that's made a complete commitment to get hydrogen. Hopefully that remains. The cost of, maybe if they're using it from blue hydrogen, it'll be fine. Use the, you know, get that down to $1 per kilogram in a decade, and that started a few years back. So that's green hydrogen. And then, of course, we've got a little bit of fun with the natural hydrogen. There are many geological processes that generate hydrogen in the subsurface. So we've got many different source rocks, and there are hydrogen seeps all over the world. So everybody is now scattered looking at these and looking for hydrogen, and it's like a new frontier, and it's brilliant. And if there's time, I have a couple of slides, if you can bear with me at the end, if you're still with me, where I go through a little bit of detail of one of the hydrogen sources that we have in Scotland, and some work we did on that as well. But of course, at the moment, it's very uncertain. We have a lovely example in Mali. They have a well that produces hydrogen that runs a fuel cell that provides electricity for the village. They don't really know where the hydrogen comes from, but it's been running for 9 years. So they're just like, oh, this is fine. As long as it keeps running, we're happy. But that is really, really cheap. We also have companies that estimate there's just hundreds of millions of resources under the Pyrenees. So they're trying to get permission to extract that as well. So this is a new frontier for geologists, and it's really quite exciting and interesting. But I'm not here to talk to you about that, even though I do like talking about it. I'll stick to topic. So I mentioned that we want to start producing our hydrogen, and we have to start producing hydrogen, and we have to start producing it to bring the costs down. Yeah, same as we did with wind. So the UK, after the invasion of Ukraine and the challenge of the gas supply, set a target of 10 gigawatt hours of low carbon hydrogen production capacity installed in the UK by 2030. Now that's 5 years away. It's like blink of an eye time. Anyway, that's our target. So to achieve that target, there are a number of funding mechanisms to support that, because we can't do it without that. It's too expensive for these new technologies. So it needs government subsidies to support it. So at the moment, in the UK, we already produce around about 24 terawatt hours of hydrogen from our grey hydrogen production, and that generally gets used straight into the refineries. It's produced on site through hydrogen refineries, with, as I say, a lot of CO2 emission associated with it. So, you know, we do already make, produce, transport, use a lot of hydrogen in the UK. But what we now have is a government subsidy, which is the hydrogen allocation round, HAR1. Now that has put forward, or is now going to fund, actually 11 projects it's going to fund. In the end, 11 made it through, with a capacity of around about 262 megawatts of hydrogen production. So these projects are starting to be built out now. Contracts have just signed, and they're going ahead now. So the map shows some of where these are. HAR2 is now underway. That was oversubscribed. They had so many more applications than they had the funding for. So again, they are hoping to really increase up to 875 megawatt hours. But HAR1 is already 2 years in, and there's not even the contracts are only just ready to be signed. That's not ordering the parts, getting them shipped over, installing them, and everything else. And HAR2 is going to be even longer than that. And that gives us 1 gigawatt hour of production. We need to get to 10 by 2030. So we really need to ramp that up, which is going to be interesting, but we shall see. And then, of course, we can move it. You know, we also need to transport it. We're looking to see how we can make it, but we also need to transport it. And there's a number of initiatives. So in Scotland, we have H2 Caledonia, that's looked after by SGN, and that's looking at developing a hydrogen pipeline from St Fergus to the Central Belt to our industrial things. And then that links into Project Union, which is the UK-wide hydrogen pipeline network. And then that links into the European hydrogen network, which is the European hydrogen backbone. So all of these networks are being put in place to anticipate the time when we're using and making hydrogen in abundance, shall we say. And then, you know, in terms of that anticipated industrial use, this is really just a kind of a first look, but we're really looking at sort of needing terawatt hours of hydrogen in our just industry. This is not looking at it in any other areas. So we're really starting to join the dots in terms of making the hydrogen, moving the hydrogen, using the hydrogen, which I think is really important. We have that joined up picture. So where's the geology in all of this? Yeah, that's what you're asking me, I know it. So the geology comes in because hydrogen, while it has this brilliantly high energy density by mass, its small mass by volume means that storing it at high energy densities is really difficult. It's really challenging. So really you can bond it to things, you can turn it into liquid organic hydrogen carriers, but they come with energy penalties. Ideally, what we really want to do is be able to store it in a gas form. And for that, we need a very large space. And the subsurface is the only place with space big enough. We just can't put those in surface tanks. So again, looking to what we think we're going to need in terms of storage. So the UK government and all the national grid sort of modelling scenarios are looking at, even if we go fully electric, so no hydrogen for heat, no hydrogen for industry, all hydrogen for heat, anything, we just do fully electrification, we're still going to need 14 terawatt hours of storage a year for hydrogen. So that in itself is a very large number. Europe is looking at hundreds of terawatt hours of storage. They're really quite big on getting energy storage and energy security, as you can no doubt imagine. Even the US, for their clean electricity grid, which may be on pause, but we'll come back, is looking at hundreds of terawatt hours per year of hydrogen storage. So where can we put that? Well, we have to put it in the subsurface. So this picture shows you discharge duration, which I think is really important, is how long can it deliver that energy against the system power. So that's kind of megawatt, gigawatts, how much power can it deliver? And of course, our traditional energy storage is in grey. So we've got pumped hydro, we've got some thermal storage, batteries, of course, flywheels, and they're really great for a couple of hours at a sort of megawatt. But I was talking about terawatt hours of storage, terawatt hours, whole magnitudes of scale difference. So this is why we need the geology, because we can start to store hydrogen in engineered lined shafts, engineered lined caverns, in offshore and onshore salt caverns, and in porous rock storage. So these are the geological options where we can, they're really the only options available to store that gigawatt and terawatt hour storage of hydrogen. And that's why, as I say, suddenly the geology comes in. So yeah, we have these different technologies which have different capacities, different power discharges, and of course, different geological requirements. So we can store it in dedicated pipelines and tanks or subsurface silos. So these are quite independent of the geology because they're just in the shallow surface. We can look at lined shafts and mine working. So for the mining sort of amongst us, there's going to be a lot of interest in that. We can also do lined rock caverns. So great, drawing on our great civil engineering expertise. And then, of course, we can look for salt caverns and porous rock reservoirs. So I'll just quickly go through all of these and put them in a Scottish context so that you can see where we are. But I guess the first thing to do is say, well, have we done this before? Is this something we got experience in? And the answer actually is yes, we really do. We've been storing hydrogen in salt caverns in Teesside since the 70s. That's just a few years ago, really, in my book. So that's been active, for a very, very long time. We also have a few in America. We have been storing time to gas. So, before North Sea gas came online, we used to get our gas from the gasification of coal, and around about 60% of that was hydrogen. So we stored that in aquifers very happily, commercially for years. Most of those storage sites are now continuing to be used for natural gas. So the hydrogen didn't destroy them. We now have pilot projects that are looking at hydrogen storage in depleted gas fields, and they've started injecting and recovering hydrogen, which is really exciting. And we have another project in Sweden. They have hard rocks. So they've built a lined rock cavern for their decarbonised steel works. So they've got that built and is storing hydrogen already. So this is really, this is all really very positive news in terms of that idea being commercially available. And this map just gives you a snapshot really of some of the hydrogen projects that are underway now. This is in the last 5 years. Yeah, there was no hydrogen really on the map, a few places, but this has all happened very, very recently. So you can see already there's over 45 projects underway or in planning for hydrogen storage. The blue color dots are salt caverns. So it's dominated by salt caverns. It's a relatively straightforward technology for people to understand, and it's very commonly used in gas storage. The orange dots and colors are for hydrogen storage in porous rocks, which we're also going to need. And then the gray ones are lined rock caverns. So you can really start to see that Europe particularly is really leading the way in terms of this. And we're not doing badly in the UK ourselves, actually, in that picture, which is good. So yeah, let me just go through each one of them a little bit in turn. So I'll start with lined rock caverns. There's also lined rock shafts, and the idea that we could use mine shafts for that. But basically, they work on the principle that they are hard rock that you dig out, and then you line with cement and a steel liner to give it the gas tight. And then the rock mass kind of gives you that confining stress or confining pressure to deliver that. So they can be quite high pressure, or well, not hugely high, but they can be quite high pressure, tend to be about 100 meters deep, sort of 60 to 80 by high and 30 to 40 meters in diameter. And they can hold around about 90 gigawatts per cavern, and you can cluster them. So you can have more than one cavern nearby coming off the same plant. They're very flexible. They can be clustered. They don't take that long to build out, 5 to 10 years. And there's many in use around the world for gas storage. And we do have that experience of the hybrid project. So lined rock caverns are quite appealing. They're particularly appealing for Scotland because we don't really have any salt onshore. And I think they're really powerful because they're not too big, because we're not really making that much hydrogen at the moment. So there's no point in oversizing we need storage that matches our development. So what we did was my colleague Kieran and I, we started delving through the BGS GeoIndex, looking at the engineering geology data and the borehole data. And we've started to kind of understand and map the strength of our rocks in Scotland to identify where we could host lined rock caverns. Now, SGN funded this work because, of course, they were really interested in how they can support their gas network. So as it transpires, we have this lovely alignment. So the graph on the side shows the project, the H2 Caledonian, the gas. The purple line is the Project Union, our hydrogen pipeline. And the red circles are the gas demand that we anticipate for hydrogen, so we can see where it needs to come. And then the green, darker the green, the stronger the rocks. So we've got a really nice alignment of nice strong rocks in Scotland. Let me assure you it's not the same in other parts of the country. So we're quite lucky from that point of view that we can do that. We also have salt cavern storage, cognizant of time. We also have salt cavern storage. These are basically sort of dissolved out, caverns that are dissolved out of thick evaporite salt deposits. Salt is a beautiful sealing rock. It's very tight, it heals. So it makes this lovely gas storage cavern. There's hundreds of caverns in use for natural gas storage. And as I say, we already have a couple in Teesside for hydrogen. So you dissolve out the salt, you make this lovely cavern. They can hold maybe up to 200 gigawatts, maybe more per cavern. And again, generally, they'll be clustered. So we have a number of gas storage sites in the UK. And generally, well, on average, there's about 9 caverns per site, but there can be more. They take between 5 to 10 years, and they can be flexibly used and cycled. So they're a really appealing option. And the UK government is funding 2, or is likely to fund 2 hydrogen storage sites in the next year or 2. And they have already said they have to be in salt caverns. So that means that they're going to be in Teesside and the other side of the country, because that's where the salts are in the Cheshire Basin and the Zechstein on the other side. So yeah, so the problem is in Scotland, we don't really have any salt onshore, that is. But we do have offshore salt. So we have potential for that. So again, we've done some work here to start mapping that out and having a look at that. So we've been through all the oil well logs and identified, looked through them all. Is there salt that appears at the right depth and the right thickness? So salt caverns can't be deeper than 2,000 meters because they close too quickly. So you close your cavern. So yeah, so we can see already on the map that we do have off the coast of Aberdeenshire, which is quite nice because it's quite near where a lot of the wind farms are going to be. We have the potential for salt offshore, but that's a slightly lower technology readiness, or it's not technology readiness, but you know, it's a bit more expensive to do a salt cavern offshore than it is onshore. And then, of course, from our own research, we're, you know, the research that we do here is starting to look at how these rocks respond to hydrogen. So we know that salt cavern storage of gas is a very well known technology. So we're not reinventing the wheel. What we're really focusing in on what are the questions or risks that are specifically related to hydrogen. So for hydrogen, we have the potential for hydrogen sulfide reactions with sulfates. So in our salts, not all salts are the same. We obviously want nice clean halite, NaCl, but sometimes you can get sulfate-bearing salts such as anhydrite or gypsum. So we need to understand whether there's a risk from that. We need to understand kind of what the impact of all the additives that we're putting in the salt cavern might have on the hydrogen purity. We need to make sure that rapid cycling is okay with the salt integrity, which it is. Microbes really like hydrogen, so we need, and they do live in salt caverns, so we need to understand that because they could consume or contaminate the hydrogen. We need to understand whether hydrogen might leak through non-salt layers that are interlaying with salt, and we need to understand the wells. So all of the work that we've been doing is showing that actually really there's negligible risks associated with any of these. So that's all good news. And then, yeah, just to kind of close off, we've also got porous rock storage. So for that, we're really looking towards depleted gas fields. It's well understood geology. It has an existing infrastructure. We can also look to saline aquifers, less well-known geology, less infrastructure, but they're still a good target, although I think they're probably better for CO2 storage. But what we're really looking for, same as CO2 storage, we're looking for a nice porous reservoir rock that will hold the hydrogen and allow it to be injected and withdrawn with ease, or as much ease as you can, a sealing cap rock, a trapping geometry, That means we can kind of produce that hydrogen, and then a cushion gas. So all gas storage operations need what they call the working gas, which is your core hydrogen, and then you have this cushion, which basically allows you to inject and then produce the gas. So the cushion gas is really important. And in a depleted gas field, it's about 50% of the entire volume of the reservoir. In a salt cavern, it's about 25%. So it's quite a big part of the reservoir, that cushion gas. And of course, in a depleted gas field, you've got the ability to use the methane as a cushion gas. So yeah, so these can hold terawatt hours, but they are geographically constrained. You know, they are likely to be dealing with those large scale seasonal fluctuations that we need for supplying that winter heat. And we have lots of use of that. So this graph just shows you the potential porous rock potential in depleted gas fields. So we developed a methodology for converting the recoverable gas from a depleted gas field into a hydrogen storage capacity, and that is a volumetric. And the graph, which shows all the grey coloured dots, are our UK gas fields, and those are the equivalent hydrogen storage capacities for each of these gas fields. What you immediately see is there's not that many in Scotland. And of course, that's because Scotland's oil and gas fields are dominated by oil. So we tend to have oil fields just because of the maturation history, the temperature it reached, and the type of organic matter that was more oil prone than gas prone. Thanks, Pat. And then of course in the southern North Sea we're looking at more gas fields. So that's that. And again, what we've been doing here in Edinburgh is really working to understand what risks are associated with that, looking at caprock integrity, looking at risks from geochemical reactions, looking at risks of well cements and microbe consuming and recovery efficiencies. Can we get it in and get it back out again? Really looking at reservoir modelling and public perception and social acceptance is a big issue. And really all of our investigations show that these risks are minimal and can be managed. And I think what's really exciting about this field is that it's really important to remember that, 5 years ago, we started these experiments in the lab. And now, instead of doing research, we are now testing rocks for companies that are going to be building out storage sites. This is a phenomenal pace of activity. It's so exciting as a researcher to be seeing what you've thought of in the lab out there in the world, being deployed in real situations, all in less than 5 years. So it's kind of cool. And then just to finish, we've really got to think about how we integrate that into our energy storage system, because it's not just about the hydrogen storage, it's also about how that links with our existing oil and gas infrastructure, which isn't going anywhere. We're still using more and more gas every year. We need to think about how it exists, how it maps into our existing electricity and gas system and into our renewable energy system. So these maps really just show you a snapshot of where our current energy systems are. And then you put them all together and you can start to see where you have alignment and where you don't. And I think that's really important. So I know this is a busy picture, but really what you can see is it's very busy around the southern North Sea, and that's a good thing. You've got salt there, you've got gas fields, you've got wind farms, you've got plenty of infrastructure, plenty of demand, and they're looking good. Scottish wind farms, not so well connected, really. And the ScotWind wind farms, which are in the bright green boxes offshore, especially the ones to the northwest, where is that electricity going to go in? I mean, the curtailment there is going to be beyond a joke. That's going to have to be hydrogen, but then what are they going to use the hydrogen for? Anyway, those decisions were above my pay grade, but I think it's really powerful when you get to see how those come together. And then just to finish, unless you want to see some more slides on natural hydrogen, which I understand if you don't, but just to finish, I thought I'd preempt some of the questions, because everyone's like, oh, but hydrogen, it's not great for this and it's not great for that. And that's true, right? If you look at it from an efficiency point of view, electricity from renewable energy is the best thing to use, right? And that is absolutely a given. So, while hydrogen is versatile and used in a similar way from natural gas, of course there's efficiency losses. You got to make it from the electricity, So it's never going to be as good as using the electricity directly, but it will never be used in a situation where you can use electricity. Why would you? Yeah, so it's not going to do that. That's like saying, you know, it's just crazy to think you would ever use something that was inefficient in the wrong setting. So no, it's never going to be used in a situation where you could have a cheaper electrification option. Simple as that. It is only going to be deployed where you've got no other option. And for that, we have to be pragmatic and accept that there's going to be efficiency losses. And I think it's really important that it makes use of that wasted energy. It's criminal how much energy we're wasting. Really, it's, you know, we shouldn't be doing that. And of course, hydrogen costs a lot to make. So yes, it's expensive. It's a lot more expensive than electricity, again. But it is worth noting that 80% of the cost of producing hydrogen is in the energy, whether that be electricity or gas, depending on the method that you're making it with. So of course, if we are able to use that curtailed wind, which theoretically could be free, if the companies are already getting paid for it, if they were allowed to release it for hydrogen generation, then that would be a significant cost saving. And as I mentioned before, there is an absolute expectation, given the investment in the production facilities for green hydrogen, that that cost will come down very, very quickly, with well below $2 per kilogram by 2030, if all goes to plan. And then there's like, oh, hydrogen, it uses so much water. You need a lot of water to make hydrogen, and you do, yeah? So, you know, to make 1 kilowatt of hydrogen, you need 9 liters of water, right? So it does use a lot of water. But I mean, really, how much water do you think goes into a power generation using a steam boiler? Let me tell you, a lot more than is needed for hydrogen. And then nuclear, whew, you need an awful lot of that. So, you know, yes, it uses water, but you know, not nearly as much water as other energy uses. So we'll actually use less water if we switch away from gas. And then, of course, we can combine it with desalination for countries where there's water shortage. Desalination is super cheap, so it's not an expensive part to add on to the cost of generating green hydrogen. And we can use wastewater. You know, in Scotland, we already produce kind of 850 million litres of wastewater a day. Yeah, so I've got a student at the moment who is taking samples from the Bowness wastewater sample, and she's analysing those to see what contaminants are in there so that we can test what they would be like in an electrolyzer, so that we can understand whether there will be cleanup needed, or actually what's probably going to happen is the electrolyzer membranes are going to get better. So they're not so fussy, because at the moment they're quite delicate, but they will become less delicate with increased deployment. And then you've got, oh, but burning hydrogen produces NOxes. Oh, it's going to be terrible for the planet. Burning hydrogen doesn't produce NOx, but yes, burning anything in air produces NOxes. So that's absolutely right at high temperatures. However, NOxes, you're not allowed to just produce NOxes that willy-nilly. You know, there are limits for that, and there are burners to reduce NOxes. Very simple. You just use a lean burn technology, so double burner, and you don't produce NOx. So it's not going to be an issue. You're not going to be burning things for NOx because you're not allowed to. So no, it doesn't produce NOx. So this one, hydrogen is an indirect greenhouse gas. Yes, it is. So we do have to be careful. I mean, it's not nearly as bad as methane, but it isn't entirely without its consequences. So what happens is, of course, the hydrogen, the OH radicals that are out there, hydrogen, they're just like the best friends ever. So they obviously immediately pair up. And what that means is that it's not hanging around for the methane. So the methane's having to pick up the dregs, and it stays around for longer, and it's all terribly sad. So, you know, that's not ideal. And then, of course, you've got, like, it's highly unlikely it'll reach it, but it is possible that hydrogen could reach the stratosphere, and then that increases water vapor up in the stratosphere, and that enhances catalytic ozone destruction involving hydrogen radicals. So, you know, that is an unlikely but possible scenario. So we do have to make sure that we're not increasing our fugitive emissions. But hydrogen's expensive. You ain't going to want that leaking. So that's going to be well managed anyway. And then, of course, public perception. You know, people don't like change, and that is challenging. And people also don't like having things imposed on them, and I totally agree with that. Who wants that? But what I think is interesting, actually, is that most of the studies that have been done so far into public perceptions and that top of the mind thought of hydrogen are generally neutral. So people are not too stressed about it, and they're quite accepting of it as a development of fuel. Yeah. So in fact, we were just in Mark and I were just at a talk this morning by a social scientist, and I found it quite interesting that they're more comfortable with using hydrogen as a fuel and storing it in the subsurface than they are with storing CO2 in the subsurface as an emission reduction. So people are, you know, somehow more comfortable with that. But it's a clean fuel, so that's it. And I can talk about natural hydrogen if you want, but I can also give you a break. Yeah.
Thank you very much.
Yep.
And yep, round of applause, please, for Katriona. And so now we have time for some questions. If anybody online's got a question, please just enter